Good morning, everyone. Um, it's a wintry Thursday in Boston over here. We got blizzards outside. But today, this morning, or this afternoon, depending on where you are, we're here to talk about what Meltdown and Spectre mean for cybersecurity in 2018. And I am one of your hosts, Patrick Londa, and I am joined by my colleague Jonathan Fortunati, who's a sales engineer for Collaborator, which is our code review and document review tool. And we both work at SmartBear Software. So for anyone who might not be familiar, we just want to make sure that we introduce what SmartBear is and the kind of solutions that we offer. So SmartBear overall, we're a leader in software quality tools for teams. So that means we have about 16 different point solutions across the software development lifecycle for whatever a development team might be needing to go tackle. So whether that's really comprehensive code reviews with our tool Collaborator, we also have testing and API solutions, as well as monitoring tools as well. So just to give you a full sense of that portfolio, so Collaborator, which I mentioned, you're at the very beginning of your development lifecycle. We have Test Complete for automated UI testing, cross-browser testing that lets you test on real devices. We have a lab out in Memphis with I think 1,600, a ton of devices. So you can try all the different variations, and then Alert Site for monitoring. And then we also have our API suite with Swagger and Swagger Hub, as well as Soap UI Pro, Service V for some server virtualization or API virtualization, and then Load UI Pro as well. So really comprehensive, individual point solutions versus sort of an enterprise offering. And then we really think it's important that all the tools that you're using should be able to tie into each other. So obviously integrations are a big component of all the tools that we offer as well. So today, we're going to go over the agenda really quick. So first off, we're going to take a look at the broader cybersecurity landscape, just see where we've been, where we are right now. And then moving forward, we're going to take a look at Meltdown and Spectre, two of the most recent cybersecurity vulnerabilities that have surfaced, that are making a lot of news. So I figured we'd break them down and make them a little bit more understandable. And then we're going to talk about the rising risk of counterfeit parts. This topic doesn't get talked about, I think, enough, but it's starting to really gain some traction in different industries as being a real concern. And then we're going to talk about the concept of establishing sort of an end-to-end peer review process, and how that might contribute to a cybersecurity protection program. And then lastly, we're gonna talk a little bit about our tool Collaborator and how it's been helping development teams sort of implement that kind of peer review process. So first off, we're going to talk about the landscape. So I think everyone sort of has a traditional perspective, and this isn't necessarily just developers, but I think the broad public has the traditional perception that cybersecurity means there's always someone in a hoodie, and they're trying to break into the mainframe, or they're doing something that companies try to prevent with firewalls, with antivirus programs, employee training, and quality coding practices. And for the most part, that's been accurate. You do sort of have those black hat hackers, whether it's anonymous or this graph on the bottom left here shows in 2016 there was that DDoS attack that took down a lot of major sites across the country. So you can sort of get a sense of how one attack can really have a broad impact. So this has sort of been the traditional perception on cybersecurity so far, and I think it's for the most part pretty accurate. And as a result of this, companies have started to develop approaches to mitigate these kinds of attacks. So whether that's decentralizing and encrypting your information, by this I really mean a lot of companies are trying to move to blockchain, whether that's healthcare or finance. I mean, really any industry where you're dealing with a lot of information that needs to be highly protected. it seems to be the consensus that blockchain is going to be the future there. And then another approach is to leverage a security tool to detect vulnerabilities. This is sort of during that development process. Our team for Collaborator, we use a tool called Veracode that lets us sort of scan everything and see if there's any vulnerabilities clearly in our development process. So that's a technique that a lot of teams have picked up. There's also penetration testing on your systems. So this could be in a lot of different forms. It could be having internal members of your team try to test your systems. It could be hiring an external agency that specializes in penetration testing to sort of pressure test your systems and see how they hold up against cyber attacks. And then I suppose another form of this would also be bug bounties that companies can put out. So you hear stories like Facebook, rewarding folks for hacking or for finding a defect and then bringing it to Facebook's attention. And then lastly, training employees on security best practices. Not all cybersecurity attacks are digital. A lot of them involve some sort of social hacking. So the company before this, I was working at a healthcare startup, or consulting startup. So we were trying to be very ISO compliant. So it was really important that whenever you leave your desk, you close your laptop. We had a shredder in the office. There's sort of different best practices that you can pick up to improve the security on a day-to-day basis of your office. So we have the traditional perception. We have approaches that have sort of picked up to try to mitigate these kinds of attacks. But we also have a changing landscape in why people are launching these attacks. So I think I'm not sure if anyone on the call has heard of this, but I think in 2017 there was a venture capital firm called Muddy Waters Capital, and they hired a penetration testing company called MedSec to test the pacemakers made by St. Jude Medical and try to find a defect, essentially try to find a cybersecurity vulnerability, and then publish that vulnerability, and then short the stock of St. Jude Medical. So this is really sort of the first public case of a company actively trying to profit off of a cybersecurity vulnerability that a company hasn't that has allowed to slip through. So this case is highly it's going to be in court for a number of years still. But I think it's interesting in that cybersecurity vulnerabilities are becoming sort of a weak point for really any development team. Because after this happened, Whitescope, which is a penetration testing company out in California, they ran some tests and found that there were 8,000 vulnerabilities in pacemakers across the industry. So what's classified as a vulnerability? How can all these companies defend against them? It's become much more of a competitive space as opposed to just having that one-off cybersecurity attack that you have to defend against. And then, so that brings us to 2018. And 2018's been already a huge year for cybersecurity, especially because of these two vulnerabilities that we're going to talk about today, which is Meltdown and Spectre. So just to sort of set up a timeline, so everyone's kind of aware of how these two vulnerabilities were made public. So Jan Horn, who you can see on the top left, who's actually only 22, which I think is really impressive. He's working for Google's Project Zero, and as part of that, he's been looking into cybersecurity, doing a lot of research. So he found the initial vulnerability back in June of 2017, and he brought it to Intel and he brought it to ARM and AMD, and said, hey, we have this problem here that's really kind of fundamental, and we'll talk specifics coming up, but he brought it to the attention of Intel and all these other companies, and those companies said, we understand that this is now this is a active problem, and in order to solve it, because it affects nearly every processor in the world, we need some time in order to go implement a bunch of patches and microcode updates, and really try to fix the problem before the problem becomes public and it becomes a risk that hackers can use this now public vulnerability to go target companies. So notified it June 1st, and all these other people on the screen have also been working on the same kind of problem, looking at the sort of design of these processors and trying to see how exactly to break them or find that breach. And it's kind of interesting that all this has sort of happened within the last 6 months, because when these processors were initially designed, I believe it was 1995. So the problems that they identified have been out there for about 20 years now. So they were initially notified June 1st. It affects processors, operating systems, web browsers, cloud platforms, and then all these companies that you see in the bottom with Microsoft, Amazon, and Google and Linux, they all actively were working to try to solve this problem. And this story finally broke in early January. So by that time, a lot of the companies have been able to launch sort of initial updates. And one of the reasons that it came out earlier than it was intended to be revealed was that Linux had to do updates, and Linux is open source, so all the updates that they were doing were publicly available. So I think some developers saw what was going on and were able to start connecting the dots a little bit. So I'm going to turn it over to John, and we're going to get into sort of exactly what are these vulnerabilities and what are some of the root causes.
Cool. Thanks, Patrick. All right. So before we talk about Spectre and Meltdown specifically, I want to lay the ground for some foundational concepts and kind of explain how both of them, what they're exploiting that makes them work and makes them so dangerous. So two things that we need to know before we kind of start talking about Spectre and Meltdown, and that's the concept of memory isolation. And the second thing is, I guess, memory addressing, is what I'll call it, or memory mapping. But so memory isolation. Let's say Patrick and I are using a computer. We both have different accounts on that same physical machine. Obviously, Patrick doesn't want me to get access to his data, and I don't want him to get access to my data. So that memory is isolated from each other. And if I run a process on my account of the computer, it won't be able to access memory or get access to files, things like that, excuse me, on Patrick's side of the computer. Again, that's the concept of memory isolation. The second concept, memory mapping or addressing. Again, if we go back to that first thing, my processes that I'm running under my account are only able to address memory that I have access to. However, there's something in the computer called the kernel, and typically that kernel has access to all the physical memory and has the ability to access that physical memory. Obviously, if I'm an attacker, that's something that I would want to exploit. And if I'm a victim, or if I'm not an attacker, I don't want that. I only want processes who should have the power to access the kernel and run instructions with the kernel to do that, to make sure that those memory isolation barriers are respected.
Sure.
So again, those two concepts, memory isolation and the ability that certain processes, certain privileged processes can access all the physical memory on a machine, or address all the physical memory on a machine. So specifically, what is Spectre and Meltdown exploiting? They're exploiting something called speculative execution, and specifically the symptoms of speculative execution. So what is speculative execution? So these processors that we have, there is physical limits to how fast they can run. And as a way to get past those physical limits and to improve speed of the processors, one thing we can do is change how the processors are actually calculating these instructions. A great example that I read online when I was learning all about Spectre and Meltdown when it was coming out was the example of a cook in a kitchen who has a recipe. That recipe has, let's say, 10 steps. Maybe steps 1 through 5 have to be done sequentially. However, step 6 isn't dependent on steps 1 through 5. we could start step 1 and also start step 6 and have step 6 going. Maybe it's put a chicken in the oven while I'm doing some vegetable prep work, right? That's going to save us time, because by the time I'm done doing steps 1 through 5, step 6 is also done, and I've sped up my execution. So in processor land, that's called speculative execution. Now, when processors perform speculative execution, again, moving forward in the instruction stack and calling some kind of instruction on the idea that it may be important later, what they do is they keep the results of that instruction in a short-term memory. And when the time comes that they need to use that information, if it's invalid, they throw it out. Again, the idea being we may go forward and we may execute an instruction that we weren't supposed to actually execute, maybe because a conditional statement didn't go down that path or something like that. So we don't need the data, so we can throw it out. However, another aspect of speeding up processors is using something called the cache on the processor. So I'm sure a lot of us are familiar with cache, but if you're not, a cache is just memory that's quickly accessible to the processor versus something like RAM, which is also fast, but in terms of the processor, slower than cache. So the idea of using cache on the processor is, as I'm executing instructions, I'm going to find instructions that I execute often. Rather than continuing to execute them and potentially pull information from slower to reach memory, I can pull it directly from the cache. So it's going to make executing that instruction faster. So again, these two things, speculative execution and storing things in the cache, designed to make processors faster. The intent was to make them faster. The intent was that any erroneous calculations are immediately thrown out. And again, the goal, make them faster. Unfortunately, there was a flaw in how these things work together in reality that was exploitable, and that's what Meltdown and Spectre are. They're two things that are exploiting both of those speed enhancements, processor speed enhancements.
Okay, interesting. So let's start to get into sort of what is Meltdown, I guess, as a place to start.
Sure. All right. So Meltdown exploits something called out of order execution. So let's go back to that example that I gave where we're looking at a recipe and we're executing step 6 of the recipe in parallel to steps 1 through 5. Now, I mentioned that the processor is going to jump ahead. It's going to perform some kind of calculations. And if it didn't need that calculation, it's going to throw it away. However, if we go all the way back to the idea of there are certain processes that could access parts, restricted memory, privileged processes that can restrict certain memory, those should be blocked from running if, for example, my user account were to try to run that, if I don't have privileges to run that. But when the speculative execution happens, there's no check on running those kinds of processes. And the reason there's no check is because we're just going to throw that data away anyways. So when the actual process thread gets to that point where it should use that data, it's going to say, oh, you know what? I wasn't supposed to have access to this. Let's just clear those buffers and get rid of that. Clear those registers and get rid of that. So the intent was that there would be no problem. We would lose that data. But what's happening, if we go back to that symptom of speculative execution, the symptom being that when we perform these instructions, the processor is going to try to put them into cache for future processing to get them faster. It's going to put the results of some of these instructions into cache. And you can use that to then later figure out whether or not you access a certain part of memory. And let me explain that. Do you mind if I share my screen really quick?
Yeah, no, absolutely.
Because I think that's a concept that's easier illustrated with just some little mock code. I'm going to drag my Notepad++ document onto the screen. All right, hopefully everybody can see that. It's not too small to read. All right, so what we have an example of here is, sorry, this is what I want to show. Here we're asking, is the password equal to ABC123? Obviously, we shouldn't be able to ask that kind of thing, but speculative execution is not testing to see if I have the permissions to do that kind of check. it doesn't care because it's going to throw it out if I don't later on when we get there. So when we jump ahead, perform this conditional statement, and if that conditional statement is valid, we'll read a pixel from an image or something like that. Now, again, when the program actually gets to that point where it's supposed to use that data, it's going to say, oh, we weren't supposed to have permission to access password, so let's throw out all the information we know about that. So problem solved, no hackers can learn about it. However, we read that pixel. And when we read that pixel, the processor put that information into cache because we may want to access that pixel again later in the future.
Sure.
So what we're going to do is run a stopwatch, and we're going to see how long it takes us to access the data for that pixel. And if it falls within a certain threshold, that means that it's coming from processor cache. And if it's coming from processor cache, that means we know password equaled ABC123, and we know what the password is for the system. Obviously, a very, very, very simple example of what's really happening. But again, the point's to illustrate how the Meltdown vulnerability is taking advantage of the processor architecture. I'm just going to minimize that, and after I give you back control. But luckily for us, there is a mitigation to Meltdown. That's something called the Kaiser patch, and that will mitigate the effects of Meltdown. It was actually developed to mitigate the effects of another security vulnerability. It just so happened to also apply to Meltdown and help us protect ourselves against from this kind of out of order execution.
Okay, interesting. So yeah, I mean, it seems like Meltdown, for the most part, has been remedied. All the major operating systems were able to make adjustments. So that's Windows, Mac, Linux, and then the browsers as well. So for Meltdown, that one has largely been remedied. But the same general vulnerability, I think, is a little bit more intimidating in the form of Spectre, which is sort of, well, there's two variants right now that have been identified. But John, I think, can we get into Spectre a little bit?
Yeah. All right, so Spectre. Again, Meltdown was all about out of order execution. Spectre is using something called branch prediction. Again, this is still speculative execution, but it's using branch prediction to do speculative execution. So what is branch prediction? The general concept of branch prediction is I will be executing, well, let me back up a second. There's two types of branch execution that Spectre is leveraging. One is conditional branch exploitation, and the second is indirect branch exploitation.
So those are the two variants.
Those are the two variants that we'll be talking about today. From what I gather from reading the paper, there are other minor variants you can make to how you're performing these things, but it seems to fall into these two main categories of conditional branch exploitation and indirect branch exploitation. So another thing that the processor will do to kind of help speed up processing to get those performance advantages is to look at a conditional statement and look at the statistical analysis of how often it branches, let's say true, right? And if it falls within a specific range or if it meets a certain statistical requirement, the processor will say, you know what, next time we hit this conditional statement, we're most likely going to branch true. So let's just pretend that we have the value to branch true, go ahead, execute those statements, and then perform whatever work that we need to do. And if it turns out when we actually get to that particular conditional statement in the program flow, it turns out we don't need it, we'll throw it away. Again, very similar to Meltdown in the sense, we think we're safe because even if we execute something we shouldn't be executing, we're going to throw it away. However, just like with Meltdown, the remnants of that is still stored in the cache. That kind of ghost of the data is still there, and we can use these symptoms to get access to information or learn about the information that we're trying to access that we shouldn't be able to learn. So for conditional branch exploitation, that one's a little bit more straightforward. And that's going to be basically training the processor to expect the conditional statement to return true. And do you mind if I share again? Now I'm actually going to show my very, very simple pseudocode, but I'm also going to show actually some real code that's from the papers that they published on Spectre and Meltdown. But this is an example of how conditional branching exploitation would work. So what I'm going to do is I'm going to evaluate the value of x against the end of memory that I have access to, right? My memory, I can't get into Patrick's, that kind of thing. And if that value is lesser than it's within my range of memory I have access to, I'll access memory at location X. I'm going to train the processor to expect this conditional, if X is lesser than end of memory, to be true. Then what I'm going to do is I'm going to put in an invalid value for X. Now, because the processor is going to do the speculative execution, it's going to go ahead, see this conditional, say, hey, we normally branch yes here, so let's just go access the memory location at location X. We'll grab that data and keep it. When we get here, the processor is going to say, you know what, I shouldn't have been accessing that memory. We'll trash the data, but because we stored it in the cache, we can start to go through and do the same things that we were doing with Meltdown, where we access the cache side channels and start to get information about the data that we had accessed to help us verify where we're getting memory from, what kind of memory we're getting, those kind of things. And that's going to help a hacker basically dump the memory from your system.
Okay.
And this is an example from GitHub that I found. I did not write this, so all credit goes to the author who did. But this is a project that you could run. You could download this from GitHub, and this is going to exploit branch prediction for Spectre. And we can see, if you just look at the comments, I'm not going to go through the code entirely, but we can see we have the victim code, we have the analysis code. So we're doing that timing kind of information and looking at the those symptoms of the speculative execution. Again, we're just going through and using the information that we have from those kind of trained branching instructions to learn more about the system and the memory, and ultimately take a memory dump of the information that we're looking at.
So it essentially tricks a quality performing application into doing something that otherwise it's not programmed to really go do from a memory perspective.
It tricks specifically the processor to do things that it, is doing for performance gains.
Okay.
Yep. Exactly. Tricks things into getting data that it shouldn't have access to. Now, the second variation of that is the indirect branch exploitation. This is a little bit different in the sense that indirect branching means my process may say, branch to the value, branch to whatever location is held by this variable or by this register. So if R1 holds memory address location 123, go to memory address location 123. Now this requires a little bit more work, because what the attacker is going to do is they're going to find the address location of specific things called gadgets on the victim computer. These gadgets are special instructions that can run to gain access to memory that the attacker shouldn't have access to. What the attacker is going to do is train the CPU in their memory space, in their valid memory location, things that they should have access to. It's going to train the CPU to expect a positive branch to register 1, positive branch to that specific memory location. Now, it doesn't matter what's actually at that memory location for the attacker, because what the attacker is going to do is it's going to run that in the victim space. Because the CPU is expecting that branch when it's run in the victim space, it's going to branch to that memory location, which for the victim contains that gadget, and the gadget's going to execute that code that it shouldn't be executing, gain access to that memory, and we're going to have the same kind of process where we are able to look at the symptoms of this kind of speculative execution to get information about the system and ultimately take a memory dump. So that's a very dangerous form of an attack, because it's really fundamentally built on the actual hardware and the architecture of the CPU chip, which is why right now there's no mitigation for Spectre. And I think you had mentioned earlier today when we were talking about this that there are some attempts to mitigate it, but
yeah, I think Google's been trying to put out a fix. I think their most successful one right now is called Retpoline, and I think that's mostly for variant number 2, which is that indirect variant. But a lot of the challenges behind putting out sort of updates to and sort of fixes to these vulnerabilities. The sort of downside is that you could take a performance hit as a result of this. So that's something that different companies have been struggling with, is trying to identify a way to increase the safety and the security while also not taking too much of performance hit in the process. All right.
I'll give you back control.
Fantastic. And yeah, I mean, there's a ton of information out there on Spectre and Meltdown. It's a surprisingly well documented sort of set of vulnerabilities, because they did have sort of 6 months between June and January to try to suss out exactly how to tackle it. But as John was saying, for Spectre, it looks like it's primarily going to be a hardware fix in the long run, while Meltdown can, for the most part, be mitigated with operating system and browser updates. So we're going to talk about something that probably doesn't get as much coverage, because this probably doesn't affect as many companies. But this is the concept of counterfeit parts being a threat from a cybersecurity standpoint. So if you're in the sort of aerospace or defense industry or automotive, or really an industry that relies on having a number of suppliers all contribute parts to your end product, that's where counterfeit parts, it becomes a concern, something that industry specialists are trying to wrap their heads around. So what exactly do I mean by this? This is going to be a very simplistic demonstration of this, but basically, for aerospace specifically, they're worried about electronic chips, and the idea that if a hacker were able to influence the design process in very small ways, they might ultimately be able to ruin the end product, causing a performance failure. So for this example, if you had a boat per se and you needed supplier A, B, and C to all bring their parts to the table in order to build it, then you're relying on each of those suppliers to have their own security practices in place in order to sort of protect that end product. Because if in this example, for let's say supplier A is attacked, but they have the proper security practices in place, that really doesn't matter as much to the success of the end product if supplier B is attacked and it's successful. So a successful attack, the hacker could change a specification on one of the parts, or something in the process that ultimately ends up damaging the quality of that part. And then all of a sudden, if you get different parts either not fitting right, not performing the way that they were intended, then the end product can really suffer as a result. So this is just sort of a demonstration of how, if you have a long supply chain, with 100 suppliers, 1,000 suppliers, even as some aerospace and defense companies have, it's really about the weak links in your supply chain, and that's going to be where the most damage can, or the most vulnerability is. So you really have to rely on all of your suppliers to implement these security best practices. So they're trying to sort of implement registries for parts and process regulations, industry to industry, to try to solve for this. And one of the reasons why hardware cyber attacks are becoming more enticing to hackers is that there's no immediate solution or update. So in this Spectre example, I mean, that's not going to be solved until all the processors are sort of turned over. It also only requires really one weak link. So if you have a button to push and that button doesn't work, that can have a major impact. And then they're also hard to catch. The supplier's view of things, they might not realize that there's something wrong until that part ends up in the end product, and then that is flagged as something really, really dangerous. And it's also not likely to be found by penetration testing. So while a software vulnerability is pretty easy to catch if you know what you're looking for, small tweaks in design documents or specifications really, there's not a good system for running a quick analysis and getting to the bottom of it. So moving forward, we're really talking about the idea of a digital thread as one of the primary approaches to trying to mitigate security across your supply chain. So this is a concept that's taken root, especially in the automotive and aerospace industries. For them, if something goes wrong, the risk is extremely high, and healthcare as well. So the digital thread is this concept that you try to connect all the silos across your development process. So connecting design and development and testing and monitoring from a communication standpoint, so that testing is able to see what design is doing, design is able to see what manufacturing is doing, to make sure that everything is going forward with the right intention, and that everyone sort of understands why changes are being made, and what has changed from version to version. So that's this whole concept of the digital thread. Right now, it's mostly being talked about from a manufacturing standpoint, but there's definitely a role to play from a software standpoint as well. So really just trying to connect all of your product development in one sort of pipeline, so everyone's able to really easily interact, communicate, and view information, so that everyone can be more aware, and overall quality can go up. So one of the benefits, easily transferable records. Obviously, if you're going to try to set all this up, a move to blockchain might not be the worst idea. But besides that, I mean, having a peer review process across all of your development allows you to have really solid and documented versioning. So for example, you'd be able to see exactly what changed from design document A to design document B. You'd be able to have your whole development team have really meaningful conversations that are also easily documented. And that's kind of where Collaborator comes in. So Collaborator is it's really, for those who might not be familiar, it's the only enterprise grade pure code and document review tool that there is. So that means, whether you're trying to review source code, whether you're trying to review design documents, or specifications or test cases, it makes it really easy to sort of get in and get a sense of what the conversation is, regardless of if it's documents or if it's code. So that allows you to sort of standardize your workflow, and reduce software defects and defects in general pretty steadily. And then because you're able to open up communication, we've seen that overall there's a shorter development time to market, which is really powerful, especially for some of these larger projects. And let's see, John, do you want to show Collaborator a little bit?
Yeah, sure.
Just
minimize
a little bit easier than some screen grabs. But essentially, you would be able to bring in different teams, show folks, what's changing, have those conversations, and mark defects really easily.
All right, so we're looking at Collaborator. One thing we do want to highlight is that we're by no means implying that if the Intels, AMDs, and our manufacturers of the world used Collaborator, that they would not have had the Spectre or Meltdown vulnerability. That was obviously a massive problem. But what we are trying to emphasize is how things like static analysis tools, those kind of automated code verification penetration systems can only go so far. And one thing they can't do is they can't verify intent. And a software review process is something that can help verify intent. And as we saw, a lot of times the vulnerability came down to, and again, this is obviously a much more complex problem than simply just performing a code review would solve. But again, it comes down to intent not matching reality, where we had some kind of vulnerability where we thought we were getting rid of data, but there was actually some ghosts of that data left behind. But we're looking at Collaborator right now, and I probably should explain what we're looking at. We're looking at a diff viewer, specifically two different versions of the same file that we have up here, looking at the differences. And the most important thing, I think, to this conversation is what we're enabling over here on the left, which is in the chat pane, which is that communication that Patrick has been talking about, making it easy for different people to come into the code review, look at specific changes that have been made, look at the conversation that's tied to that specific change, and look at the questions that have been asked, leave their own questions, answer questions, keep up on those conversations, get a high-level view of all the different files and how they relate to each other in the materials section, and also making sure that we have the right people added to this review. If I go over here to the participants section, we do that by making it easy to add things like groups to reviews or having set up automatic subscriptions and stuff like that. Again, all working together to pull people into the code review so we can make sure the right people have their eyes on this. We have the right checks and balances and a process around, verifying intent and looking at our changes.
So for example, you could have someone from the security team jump in on most of these reviews, right?
Yeah, great example.
So you could build out a template that says, for these types of reviews, we want to make sure at least one person from the security team has sort of taken a pass. And there's also custom checklists that you can establish.
Exactly. So you can have a security checklist. And you could even set it up so it says every time I upload code from this file location, automatically add the security group to my review, or Joe from the security team.
Yeah, and those review groups are really powerful. So it's sort of different than if you're doing a pull request or if you're doing your document review sort of via email thread. You're able to create review groups. So you could have a development group, a security group, really customize these different teams to fit whatever workflow makes the most sense for your group.
Absolutely. Is there anything else you think I should show in here, Patrick, or you think that's
I think that sort of gives a sense. But for anyone who's interested, we're more than happy to provide personal demos. And John can sort of walk you and your team through how Collaborator could fit into your team's process, whether that's for documents or for code. And we also have a free 30-day trial on smartbear.com as well. So feel free to jump in and start a trial and get a sense of how this could maybe fit into your ideal workflow.
Yep, definitely an important piece of the entire puzzle of putting together a product that doesn't have security or minimizes the amount of security flaws that are in the product. Because can't minimize everything. It can't be 100% perfect, but the goal is to reduce them as much as possible.
Yeah, and I think because development teams and product development in general are using so many tools, you might be using Jira for project management. You could be using a repository as part of your development. It's really important to be able to have one source of truth for things. So I think that's one of the powerful things that peer reviews can offer, is that for every change that's made, you can find that conversation in one place.
Yep.
All right. It looks like we've got George Smith who has raised his hand. So, at this point, we're happy to take any questions and answers.
So I went ahead and posted the question in the Q&A.
Okay.
Specifically, it's about commenting outside of changes. I've used other tools before that won't allow me to comment, refer to a line that wasn't changed, but that causes a problem in the change line.
Yeah, absolutely. John, can you get into that?
Definitely. We're not going to restrict you about when you can leave comments. It's going to get you a better review for me to leave comments and go to this old webinar review. And then materials. That's actually a bad review, but we don't restrict. You can leave a comment any line that you want at any point that you want. We'll just use this one. Geesh. None of these reviews have materials except for this one. I was trying to avoid using it, but I'm going to here. So for example, this line has no change, and I can leave comments that says no change. And I can link to other lines here. And that'll create a link to that line that will then go there, even if there's not a change there. So I could say on line 42, this affects the change made on line 53. So I can kind of have that linking. And it's not going to require, and again, these are real-time chats too. So if Patrick was in another office, we could be having a real-time chat using these chat boxes.
Yeah, and that makes it really great if you're working on a distributed team.
Thank you.
All right, thanks for the question. Yeah, I mean, if anyone else has questions, feel free to enter them into the Q&A box, or just raise your hand as well, and we'll be happy to answer.
We did have a question earlier about mitigating, or how can if I'm a regular PC user, if I'm kind of a layman, how can I protect myself against the vulnerabilities of Spectre and Meltdown? I did answer that offline, but I guess I'll answer that online for the benefit of everybody else.
Sure.
In my research, I really couldn't find much. There isn't like the do this one thing that will protect you kind of scenario, but it seems like that OS developers, hardware manufacturers, the people who are putting out a lot of the tools that we're using in our day-to-day lives, they're putting out updates. And so I think the biggest thing I can recommend, based on what I've learned through this whole thing since it came out, is that just apply the updates in a timely manner. Use safe browsing habits. I personally would avoid clicking random ads on Facebook, stuff like that. Don't go to websites that don't have an HTTPS, aren't a secure connection, even though those can be also, I guess in theory, those could be compromised. But again, just safe browsing habits and making sure to be timely with the updates as they come out from your different providers.
Yeah. I think now is probably as good of a time to actually comply with all the updates and make sure that when you get that reminder, you do push that to an update. Because
don't click the remind me in 24 hours button.
Yeah,
every 24 hours.
Yeah, I think I've been doing that for a couple of weeks now. But I'll definitely change that now. Yeah. So if anyone else has any other questions, feel free to reach out to either John or I, and we'll do our best to give you some answers. And again, we do offer personal demos for Collaborator, and there's a free trial online. So I want to thank everyone for joining us today. And yeah, have a great day.
Thanks, everybody.
Take care.